and I am 1 month, I think less than 1 month, year student, PhD in Heidelberg University. As you understand, I just started my PhD, so I can present some really good results. But instead of it, I can, what can I do? I can make a review of some articles and try to summarize what topic will I do in my PhD. At first, we will start to explain what actually this object, the first star, is, and we make a little bit stop to discussing how to find it, and speak about modeling of the first stars. The first stars, also called population 3. It is really interesting, but about this is later. Actually, this will be only one model with which I will be working, and these articles is articles from my scientific supervisors, I think, so it is the most recent. At first, we stop and ask a pretty simple question. What the first star is? Actually, in the start of the universe, after, like, I don't know, after the first seconds of, after Big Bang and all of this recombination stuff, ionization, or dark ages, we have a mostly homogeneous and isotropic universe with some baronic matter. There are some gallium, there are some hydrogen, there are like some freely levitating particles, and actually some isotropic dark energy and not so isotropic dark matter. And our composition after this Big Bang in this stage of this gas that we call primordial gas is like 75-76% of helium, of hydrogen, and nearly a quarter of helium. So, but there wasn't any other elements, which astronomers call metals, even if it is not metal. For example, neon is also metal. And the first, these first stars, we can say that it should be absolutely metal-free. We have this property as metallicity in star, where we have observed some really poor of metal stars. It is population 2, and our sun is belong to population 1. It is like metal, pretty rich star, and actually it's the most convenient star in our local like bubble, I don't know. So a population 3 star, what we can say? It is metal-free. It is just formed from some primordial gas. What can we say next? Firstly, when some observations and not observations, some modeling of the first star is appeared, everybody said that it will be like a one really big star. Like somebody said that it is like 10 in a power of 5 big star that could be a seed of a supermassive black hole, and everybody said that it will be really big. But actually that modelings wasn't so, they hadn't so good resolution. And we have modern modelings of many of authors, and actually this modelings show that this primordial gas is highly fragmenting, so it can be stable in some point, and everything we can forming this star, we form this third population star, we form not one big star, we form a few small stars, like in a multiple or binary system. So this one more high resolution, modern modeling. So like we always have, where is my, it's not one star. It is a plenty of star. It's some small cluster. It is or binary or multiple, or like, for example, we have some instability in dark matter, how and all the baronic matter is like flowing to this dark matter over density. And we have some small primordial clusters. We don't have still galaxies, but we have primordial clusters with some of these systems. Next. And what's about mass? Actually, yes. We see, like, on the high redshifts, we see like big quasars of 10 in power of 9, really bright objects with 10 power 9 mass of solars or solar masses. And we ask ourselves how it could be formed, because like if we have like these small masses, calculations and modeling saying to us that these primordial stars, these third population stars, was even smaller than, for example, stars of our main sequence. For example, on the left part, you can see like some cumulative masses, and they are definitely smaller and from some multiple articles. And seeds of these stars, hypothetical, it would be like 10 in power of 2 solar masses. But and if we try to calculate in what time it could be created, like a big quasar with 10 in power 9, we can decide that the age of the universe will be not enough. And actually, maybe it is one of the purposes that we can say that actually first stars couldn't be seeds of supermassive black holes. But what it was, we don't know, maybe. And it is a really huge field of research in the future. Actually, so yeah, we can say that it is reaching, that it is hypothetical models. And yes, this variety of masses are really huge. And what next? Where we can find it? If we look in a near bubble, we can see that like our redshift is near 0, and we don't care about it. We'll use some different distances measuring, for example, parallaxes or some non-relativistic Hubble law, and with any assumptions. But when we go deeper and deeper in a deep space, we start to, it is in some point there will be convenient us to speak not about parsecs or kiloparsecs, megaparsecs, I don't know. It is convenient for us to speak about redshifts. So like, and we can say that this population 3 stars was formed on, started to form like on 30, when redshift was like 30 from the point then we observe now. And population 2 stars, metal poor stars, started to form like 15, 20. So between like 20 and 30 redshifts, so we have like third population should be like dominant. But actually we have our Hubble ultra deep field that it is on 7 or 12, like from 7 to 12 like redshifts. So yeah, we can find it's in these redshifts, for example. But how can we observe it? If it is less than solar mass, it is quite small star, it could survive to our days, for example, and we can find it more near. There are some probability, not big, but there are. But so we wait, for example, some new stellar archaeological surveys, for example, to, for example, Webb telescope. It is like quite new, and there are some. Actually, this one Webb telescope and more calculation and observation can help us. There are some indirect methods, like from the global 21 centimeter signal or gravitational waves. Actually, I think my PhD will be devoted to this gravitational waves method, but I still did not get it at all. Not at all, but in some particular. Okay. So, yeah. So we have some model of what object it will be. What next? Actually, the computer models who can help us. And next, I want to speak about like a little bit. I don't know how many minutes it is left for me to speak. Can you please guide me? No? Okay.
For 5 more minutes.
5 more minutes. It's perfect. I have 5 more minutes to show you some difficult plots. Actually, we have some semi-analytical models. So what is this semi-analytical model? The numerical models require really high computation time, and it is quite heavy, and we need some clusters, and we need some, I don't know, what else? We need some supercomputers to calculate all of these numerical things. And semi-analytical model is pretty easier. I can just install it my laptop and try to reproduce all their plots that I've seen, for example, in article, and maybe plot something more. This program, it creates this dark matter open-densities to which this baryonic matter can flow inside and form some like genes. And then it will be genes instability, other instabilities, and forming big amount of solar-like mass stars with some plenty of variety of these masses. And it's like it based on this like a pretty stochastic dark matter merger trees. Actually, and then it is one of my most favorite plot because it shows a history of the universe. For example, in some point, you can see this orange line. We can see the formation of third population stars, and the light blue line, it is the forming of second population of stars. The red and blue lines, it is hot and cold gas trying to reach some equilibrium. So like we have some third population star supernova that explodes in some way, and it explodes and leaves some feedback. So there are already some metals, and these stars and this gas is cooling slowly down to new stars could form. And actually, the forming of stars is highly, accordingly, highly connected with ability of this gas to cool. So here we can see like how metallicity has developed. Of all the universe who developed in one. Actually, yes, it is for 1 gallon. It is 1 gallon, but I'm being too epic. Okay, how it is its evolution through their age of some mega years. This is I should mention that it is cumulative masses, so some stuff that had been formed, but nothing. Get, for example, out. Okay, I need to be quicker. We can make more plots, and for example, this one I reproduced from this code semi-analytical, and for example, we can say from the left plot that we can find like 10 in power 4 in mean third population dominated halos in some redshifts of still 5 to 20, for example, and for more like we can be more precise and say that on the redshift 10 we expect to see mostly like these halos of like in the middle of 10 in power 3 and 10 in power 4. So, for example, this size of these halos, third population dominated, for example. It's just examples. It's not like results. It's examples. Actually, we can provide really many stuff with this code, And this is be the thing that I will be doing the next 4 years. Thank you very much. It is time for your questions, and I don't see you, and I want to see you.